Lovely. All right. Well, let's get going then. I'm happy to introduce Brian Macdonald. He's with us today. He is senior lecturer and research scientist for the Department of Statistics and Data Science at Yale University. He is focusing on statistics and data science education, sports analytics, and environmental data science. He was previously the director of sports analytics at ESPN and director of hockey analytics with the Florida Panthers Hockey Club. He held faculty positions at West Point, Carnegie Mellon University in my hometown of Pittsburgh, Pennsylvania, University of Miami, and Florida Atlantic University. So I'm going to encourage everybody to stay muted during the talk. You can have your video on or off if you'd like. And as we go along, if you want to put questions into the chat, that would be fine, but we'll do some Q&A at the end. And Brian, I'll go ahead and let you take it from here. Thank you very much.
All right, great, thanks. Can you hear me okay?
Yep, sounds great.
Okay. Hi, everyone. As Russ said, I'm Brian Macdonald, currently at Yale University in the Department of Statistics and Data Science. And I guess what I was going to sort of talk with you about today is sort of just sort of like how I got to where I am right now. What was the journey? What kinds of things in sports analytics did I do? All the way back from basically the first thing that I can remember. And then, sort of, in between talking about, all that stuff that had gone on in my career, I talk about some of the projects that I've worked on. So I'm going to go all the way back to college. So I went to college at Lafayette College in Easton, Pennsylvania. And I studied electrical engineering. And I'm not going to spend that much time in college, actually. But when I went to grad school, I started in electrical engineering as well. I started in a PhD program at Johns Hopkins University in electrical engineering. After a semester, I realized, well, the things that I really like are all the most mathematical things in electrical engineering. So at that point, I decided to switch to mathematics. And so I switched to mathematics, probably not fully realizing how theoretical this mathematics degree was going to be. I imagine I probably would have been better off, at least, as far as what I'm doing now, I would have been better off like that statistics type program. But that's what I did. And, I learned a lot there. And that's when I started thinking about sports analytics as well. So probably early 2000s is when I really started thinking about it, assuming you count fantasy sports and doing some data analysis for the purposes of winning fantasy sports leagues. If those count, then I probably started, back in 2001 or 2002 or something like that. And so also during that time, that was kind of like around when Moneyball came out, and there was a lot going on in baseball, sabermetrics revolution, and I was following the website baseballprospectus.com pretty closely. And then eventually there was a similar website, hockeyprospectus.com, that came to be, and started following what was going on there. And so, I always loved math from a pretty young age. I don't know how young, but at the age of like 3 or 4 or 5, I was, my parents would say that I was very into numbers. I wanted to know all the numbers. So, but from a very young age, I was interested in math, and I've always liked sports. And so this is like an obvious overlap of those two things was something that I was starting to get interested in. I didn't really have a whole lot of time in graduate school to start doing extra sports analytics projects or anything. And it wasn't really related to what I was doing for my PhD program. But there was a course offered in the applied math department called Topics in Operations Research with Applications to Sports. And so I saw this and I decided to take it. Well, I audited it because, again, it wasn't really something that was a focus of my program. So I decided to audit it. And so I got a lot more exposure to some of the sort of sports analytics models that had been done in the recent past, and then all the way back. I think we were reading papers that were published in the starting in the 1960s or something like that. So, but that was a good course to audit, and in that course, I got the idea for my first hockey analytics project, which was adjusted plus minus, and so I remember distinctly after defending my thesis, basically like the day after, I'm like, I'm taking a break from this stuff and I'm going to start doing some hockey statistics stuff. So, so I did start with this, adjusted plus minus model. And at the time, I didn't know statistics really, but I knew ordinary least squares from like a linear algebra class, and I knew how to use MATLAB. So, so the most early adjusted plus minus model that I built was done in MATLAB, and I had to use like the department's servers because the matrix was huge, and the operations I just couldn't do them on my own laptop at the time. So that was sort of I guess I would consider that adjusted plus minus. If you don't count fantasy sports stuff, then this adjusted plus minus model was probably the first quote unquote real project that I worked. And so basically this model is it's a huge regression model that estimates the impact that a player has on the outcome of a segment of a game. And in the case of hockey, which is the first sport that I did this in, it's basically how does the player impact the goals for per 60 minutes and the goals against per 60 minutes when that player is on the ice versus when he is not on the ice. And I guess I didn't mention that I got the idea from basketball. So in that topics and operations research with applications in sports class, there was another student in there who followed basketball analytics very closely, and he told me about, I think the first one that he showed me was the Rosenbaum blog post on adjusted plus minus. So, so that's where I got the idea. Basically, I just changed the word basketball to hockey. I turned points to goals, 48 minutes and 60 minutes, and call it a day. That's quite an oversimplification, but really the early model was very close to the early basketball models that were being done at the time. At the time, it involved a lot of scraping. So there were no packages at the time in R or Python, as far as I know, that was pulling this data. So I was starting to get really good at scraping data from the web during that time. So I was learning R. I should mention that this all started when I was a PhD student, but I really started getting going when I was a professor at West Point. Basically, after I published the work that was related to my PhD thesis, I did a pivot full time to working on sports analytics stuff, and this was the first project. So I was learning R at the time. I was getting really good at scraping. I probably was not aware of a function called read HTML table at the time, so I was doing lots of scraping using regular expressions and stuff like that. So I probably spent way more time than I needed to, but it actually was really good as far as developing my coding skills. And so the first models were just multiple linear regression, and there's lots of issues with this. Sort of knew it at the time, but I spent so much time scraping that I didn't want to worry about all the issues with using multiple linear regression. I just wanted to get it out there. But later on, did an updated one using ridge regression, which was also inspired by basketball. And then I never did Bayesian regression in hockey, but I did that in basketball, which we'll talk about a little bit later. So this is really, this is the first, project, quote unquote, real project that I worked on. There's a lot of learning had to be done. It took a long time, but it was a good first step. And here's just an example of the design matrix for a just a plus minus model. This actually is a very simplified version that comes from just one game. I think this is actually a basketball game. But just to give you an idea, all of the columns are players. All of the rows are segments of the game when no substitutions have been made. And so you can imagine it's probably actually smaller in basketball. In hockey, at most there's a shift that's 35 to 40, 30 to 45 seconds long. And so you have a new row of data every time there's a substitution being made. Every time there's another set of 5 players on the ice for either team. So this is a matrix for just one game. And if you imagine, hundreds of players in the league, at the time, 1,230 games a season, and several hundred rows per game, this matrix gets pretty big. It's not bad for like today's computers, but back then there were some challenges fitting this matrix into memory. After I kind of worked on the adjusted plus minus models, at some point, I think it was around 2012, the NHL had announced that, first of all, that Atlanta Thrashers were going to move to Winnipeg, and the Winnipeg Jets would be a team again. And so the Atlanta Thrashers were in the Southeast Division, the Winnipeg Jets probably, they stayed in the same division for a year, I think, but long term, it wasn't going to make sense for the Winnipeg Jets to be in the Southeast Division, which contains teams like teams in Florida and Carolina at the time. And so we knew the NHL was going to sort of realign the divisions. And so talking with a colleague at West Point, Bill Pullyblank, we started to work on this project, which is basically trying to answer the question, what realignment would minimize league travel? And so this might be a question that a league might be interested in. I guess I should go back to the title of the talk, which was we're talking about data science problems and that are interesting to sports teams, sports leagues, and sports media organizations. And so here's one of the ones that could be interesting to a league, and that is, what kind of realignment, which teams should go in which divisions in order to minimize the travel that they'll have to do during the season. So if teams in the same division play each other more often, realignment matters. If you have a perfectly balanced schedule, then the realignment doesn't really matter. If every team plays every other team the same number of games, kind of doesn't matter if you're in the same division as teams that are close to you. But if it's not completely balanced like that, then the realignment does matter. And so we decided to try to answer this question, and certainly the league is not basing their realignment decision only on, how far will teams have to travel. They had other considerations, like they wanted to maintain some traditional rivalries. So like they wanted, for example, the Philadelphia Flyers and the Pittsburgh Penguins to still be in the same division, even if some optimal realignment said that they shouldn't be. And they also wanted, certain teams to be in the Eastern time zone and things like that for the purposes of TV and TV ratings. But we wanted to focus just on this, and it was a nice optimization problem. And basically, our approach can be summarized with basically just like a couple animations. So our approach was to take straight line cuts through any pair of cities in a league that split the league into 2 conferences. And this is just showing all of these possible straight line cuts that you could take. And then after you do this, you can, within each conference, you can do the same thing to split them into divisions. And so if you do that, here's just a selection of some of the possible realignments shown in this animation. I think this is just like the top 10. But we did this and we got thousands of possible realignments. And basically we could we had an estimated distance traveled for the entire league in a season, given that realignment, and then we could sort the realignments from shortest distance traveled to farthest distance traveled for the whole team. So it's like the sum of the distances that each team would have to travel. And this is kind of a nice approach because instead of ending up with just an optimal solution, which would be like the shortest distance traveled, the realignment that would lead to the shortest estimated distance traveled, we had thousands. So if there were other constraints, such as the ones that I mentioned before, like we want only realignments where Philadelphia and Pittsburgh are together, you could sort this whole list and then find the top realignments that satisfy those additional constraints. So you'll notice like some here, you know, there's some where Pittsburgh and Philly are not together, and some where they are together. It might be kind of hard to tell with how fast the animation's moving. But we can easily filter those out. We can filter out ones where Florida and Tampa Bay are not together, because some of them actually had those teams not together. I think that's all I was going to say about that one. So at some point, so I joined West Point after my PhD program, and I stayed there for 6 years and sort of did that type of research during my time there. At some point, towards the end of my tenure at West Point, I sort of got in touch with the Florida Panthers through a friend of a friend of a friend. A gentleman by the name of Vinny Viola had purchased the team. He happened to be a West Point grad, and that's kind of how I got connected with him, you know, through a friend of a friend of a friend. And eventually got an offer to go down and do hockey analytics full time for the Florida Panthers. And so, so I decided to, you know, I guess I should back up a second. The whole reason I went to get a PhD in the first place is because I really wanted to teach at college. And so that was my original goal. At this time, I was like, I mean, I really enjoyed what I was doing, but I thought it would be fun to take a little bit of break from that and go into industry for a little bit. I figured I would always come back to academia at some point, but I thought this would give me good, you know, sort of like hands-on experience working in industry. And I thought I would enjoy it at least for a time, and then I would eventually come back to academia, and all the things that I learned I could bring back with me to academia and in the classroom and just in my interactions with students. I can sort of share what I learned from my experiences in industry. So during my time there, I spent a lot of time doing hockey analytics and also business analytics. So I can't talk as much about the hockey analytics stuff that I did there, but I definitely did adjusted plus minus related things there, for example. I can talk a little bit about the business analytics problems that I worked on. So one of the things that we did a lot of is trying to predict demand for games. And so, you know, a lot of what I did was work with the sales team and the finance team at the Panthers. And so, you know, ticket sales is one of the biggest sources of revenue, and that's something that we kind of wanted to work on, ticket pricing and other sales-related decisions. So one of those things was trying to predict demand for games. You know, this could be used for a variety of reasons. You know, we might want to raise prices if we anticipate a game being more popular than another. We also used it to estimate how many staff we would want in their arena during a game. So if we knew the game was going to be very high demand, high attendance game, we would want to staff it differently. So there's a couple of reasons to do that, but basically we used a bunch of information like the day of the week, the month, opponent, you know, whether or not it was a holiday, how many home games have there been recently? Because if there's a lot of home games in a row, attendance tends to go down a little bit for each one. But if it's the only home game in 3 weeks because of a long road trip, attendance tends to be a little bit higher during that time. So we used all that information, and at the time when we started, there was no, there wasn't really reliable internal data. There wasn't really a big overlap with the person that was doing business analytics, that kind of stuff before I started doing it. So we actually, in the first year, we used all publicly available data, publicly available attendance data that I had scraped before anyway, because I was scraping box scores for other hockey stuff that I was doing, even before joining the Panthers. So we were using publicly available attendance data on NHL.com to do this model. Eventually, after a couple of years, we started using the internal sales data as well. But that's what we kind of had to do in the beginning. You know, there have been different projects over the course of my career where we've made heavy use of publicly available information, and it's been very valuable. So, yeah, so that was one of the projects that we worked on. And then the other thing that kind of just wanted to talk about a little bit was we worked on just analyzing our customer data. So we had a bunch of customer information, you know, including their address. And we just wanted to plot, you know, people were looking at customer information by zip code and, you know, sort of just showing a table with zip code and then number of season ticket holders who were in that zip code and stuff like that. And that, you know, that worked well, but, you know, you kind of miss out on some of the spatial information if you're just looking at a table of numbers like that. So we wanted to plot it on a map of South Florida. And so here we have where our arena is located. Well, it's more like right over there. It is not in the Everglades. These are the Everglades here, but it's right around here. These dots are where our season ticket holders were located. And the map in the background is colored by driving minutes to the arena during evening rush hour. So you can use Google Maps API and pull this information. And so we had, you know, I don't know if you can see these regions here, but these regions are all census tracts. So we found the driving distance from the center of each census tract to the arena during evening rush hour. And so that's what it's colored by. So like the green here is, you know, the blue and the green are like 10 to 20 minutes to the arena. We chose driving time, not driving distance, because there are a bunch of huge highways in the area. And if you live close to a highway, even if you're further away, it's going to take you less time to get to the arena. But we can kind of clearly see it was kind of maybe a little surprising how many of the season ticket holders are really in this, you know, 15, 20 minutes away region here. There's certainly a lot of season ticket holders elsewhere, but a huge portion of them are right here in that little area. And you know, we noticed a few other interesting things by plotting this data. You know, interesting things like, you know, for the Montreal Canadiens games, there was a certain area of South Florida that was lit up, and that happened to be a French-speaking area of South Florida. Just interesting little things like that that were kind of fun to actually see in the data. Not like super surprising, but it was fun to see those things in data. Okay. So also while I was down in Florida with the Florida Panthers, I was an adjunct professor at University of Miami and Florida Atlantic University. Taught a summer sports analytics, like 1 credit course at Florida Atlantic University. Co-taught it with Dennis Locke from, at the time he was with the Miami Dolphins. He's now with the Buffalo Bills. But we also worked on student projects there with University of Miami students. And so one of the projects that we worked on, I think I'm not going to spend a ton of time on this, but it had to do with optimizing the NFL schedule. So like, how do you create a schedule that maximizes how many interesting games there are at the end of the season? And it turns out, like, you don't want to have division rivals playing each other in the last week of the season. But in the interest of time, I think I'm not going to spend too much time on this one. But yeah, so my So I worked on some other projects also at University of Miami. A lot of those were related to Florida Panthers business analytics problems, similar to the ones that I just talked about. So after that, I moved up to Connecticut to join ESPN. And so I was with the ESPN analytics team. And at the time, I actually, I was planning on staying in academia at the time. I did not want to work for a team again. But I figured this opportunity at ESPN came up, and I decided to take it. I thought it was a nice balance between academia and sports. One of the things that I liked about it is that I would be able to talk openly and publicly about the work that I was doing. And there was a big team also at ESPN, so there was going to be a lot of people to talk with. That is, those things are not always true when you work for a team. So there's a lot of pros for working for a team, a lot of benefits. I had a lot of cool experiences. I met a lot of famous people, at least famous in the hockey world. I met Wayne Gretzky and Bobby Orr and stuff like that. I guess so there's a lot of cool things that I got to do that I wouldn't be able to do elsewhere. One of the drawbacks is that, especially at the time, most teams had like one person working on analytics for them. So we had some part-time consultants focusing on an amateur player projections. But I was like the one full-time person doing hands-on analytics. I mean, there's other people that I would talk with about the analytics and so forth, but I was the one person doing the hands-on coding and stuff like that. So I kind of wanted to be in a situation where, I could talk with other people about what I'm doing and collaborate with other people and so forth. And so ESPN seemed to like it would be a good balance of those things that, I'd still be working in the sports industry, but I would be able to do stuff publicly and collaborate with other people on the team. And so one of the first things that I worked on was NBA player ratings. So this is something that teams care about. I mean, this is one of the things I focused on with the Florida Panthers. Teams care about this because they want to evaluate player performance for the purposes of making player personnel decisions. Like, should we trade for this player? Should we sign this player? And so on. So why ESPN Analytics cares about this? Well, media should care if they want to talk about decisions that teams make. And if teams are using analytics to make decisions, then you want to understand what kinds of stuff might they be looking at internally when they're making this decision. And so this was, this is why the ESPN analytics team was formed in the first place, many years before I got there. That was one of the main reasons that it was formed, because teams were using analytics. And if you're going to talk intelligently about the decisions that teams are making, you probably want to have an idea of what kind of analytics they're using internally. So that's a big part of the reason why we want to have NBA player ratings. The other reason was we were going to redesign basketball power index, which is like the team rating. And we, in the past it was just team based, but we wanted it to be player based because players matter a lot. Player injuries, player trades, and so forth matter a lot in NBA as far as how well teams do, more so than any other sport. The stars matter a lot, have a huge impact on the team, more so than in other sports, except maybe like the quarterback in football is probably around the same level. So that was another reason. But so we redesigned NBA Real Plus Minus. And so this is like a Bayesian version of the adjusted plus minus stuff that I was talking about before. For NBA players, we kind of redesigned it to incorporated some of the player tracking data that was available. And then we, previously, I think, I don't remember when it went back to, but we went back several more years, back to 96, 97. And, it just gave us a player rating for players for each season back to the 96, 97 season. And here's just a quick comparison that we did at some point between LeBron and Giannis. We could also do things like go back to some of the Jordan years. So that was kind of cool. Unfortunately, now I think there was some issue after I left ESPN. Like 2 of the 3 people that were working the most on Real Plus Minus are no longer at ESPN. And so they had some sort of issue with data that they couldn't figure out and had to revert to an older version of Real Plus Minus. So the one that's up there now is not the one that I worked on, but you know, it's still it is still there and being updated nightly, I think. So another thing that we worked on a lot was team ratings. Like I mentioned before, this is, you know, might be interesting to teams because they want to know, you might want to know what your season outlook is, you know, at the trade deadline, how likely is it if we make the playoffs? You know, if we trade for this player, how likely is it that we'll make the playoffs? Things like that, or how likely is it that we'll win the championship if we do this? Things like that. So in order to answer those kinds of questions, and you know, the media has the same reasons for wanting to know team ratings because the media, you know, at ESPN, we would want to know what the teams are thinking when to make these decisions. So in order to answer any of these kind of questions, you kind of have to have some sort of team rating or a model for predicting the outcome of games between two teams. So we had a collection of models for several sports that involved, you know, estimating how good a team is, making game predictions, and then with predictions for every game, you can simulate entire seasons. And then you can come up with like, and you can simulate this like, you know, thousands of times. You can come up with expected win totals and things like probability to make the playoffs, probability to win the championship, and so forth. If you also simulate the playoff bracket. And then at the time that I was there, sports betting was starting to become more of a thing and like legalized in more states and so forth. So we started to focus on betting metrics as well, which most of which were derived from these other things that we were creating. So, for example, if you have an expected win totals, or if you have a distribution of win totals for a team, you can imagine that might help you decide whether or not you're going to take the over or the under. And so, here's just an example of the output of one of these models. This is not a model that I worked on, but this is the football power index. So these are the expected win totals, or the chance that each team would reach each win total in. It doesn't say the year here, but I guess it was the 2020 season. But it was one of the years where the Chiefs and the Ravens were clearly 2 of the best teams. I think this was the year that the Bills broke out also. So it would have been kind of unlikely for them to get 12 or 13 wins. I forget exactly how many wins they got, but so they were a team that overperformed their projections. And here's just an animation of just showing how these kinds of projections can be updated over time as games are being played. This is one that I actually made before ESPN. I chose the 2017 season in part because I'm an Eagles fan, so decided to choose the NFL East division, or the NFC East division in the 2017 season. But we just see the expected win totals are being updated over time as games are being played. This is week down here. And then we see the distribution of win, or like the probability of the teams getting each number of wins here over on this side. And we see that updating over time too. Another thing that we focused a lot on in 2020, because there was not a whole lot of sports content, if you recall, starting around mid-March of 2020 through a lot of the summer. So one of the things that we focused a lot on during that time was the NFL draft. And so a couple of folks on the analytics team, Brian Burke and Hank Gargiulo, worked on this NFL draft projections model. And so one of the things that I kind of wanted to do was try to see if we could visualize the results of this thing. And so that's one thing I worked on. And basically this model estimates for each player and for each pick number, what is the probability that that player will be selected at that pick. And so we see an example here with Tua. Was not likely to be picked with one of the first two selections. I believe the most likely for pick one was Joe Burrow, and then number two was Chase Young. And then we see here at picks 3 and 5, he's more likely to be picked. So this, it's not a perfect monotone decreasing or bell-shaped curve here. We have these two weird peaks at 5 and like a little bit of a lower chance at 4. That's because the model incorporated team need. So I don't remember who team 4 was, but they did not really need a quarterback, whereas teams 3 and 5 did. So that's kind of why we're seeing peaks like that. But these chances to be selected at each pick could be updated over time as the draft was going on as well. And so that is what this animation is showing. This is for Tua. As selections are being made, all of the probabilities change over time, and then he's eventually selected here at pick 5. So we could look at this for several players at once. So here's Tua right here. So you can see that, and these are all the picks 1 through 10 here. So you can kind of see the peak here at 3 and 5 for Tua, like we saw before. But now we see a bunch of other players here too in the top 10, here, and where they're most likely to be picked. So we saw Joe Burrow and Chase Young, 1 and 2, and so on. And one of my favorite animations, I think, that I've ever made is animating this. So here is a huge list of players. This is like the top 64 players, and these are picks 1 through 64. And this is just showing these updated probabilities as picks are being made over time, and just how those probabilities are changing. So you'll see like the weird looking rows are usually quarterbacks, like Jordan Love right here. Kind of looks funky in the beginning, lots of peaks and valleys. And down here, I don't remember who that was down here, but yeah, any of the weird looking rows are probably quarterbacks. And I think I'll skip that one in the interest of time. And so one of the other things that we had to deal with at ESPN was a whole lot of changes to sports after sports returned. And so one of them was the playoff format in baseball. So there's a new format. There's an article here about it. I just thought I'd share a couple of the things that we worked on. So we worked on these numbers. So this is just comparing each seed's chance of winning the World Series under the old playoff format and the new playoff format. And of course, the 6th, 7th, and 8th seeds have more of a chance because their chance before was 0. The 5th seed and the 4th seeds, their chances went up, and then the 1st, 2nd, and 3rd seed are less likely to win the World Series under the new format, basically because there's more teams in the playoffs. And this is another figure that just compares for each of these teams that had the biggest changes either in the positive or negative direction in their chances to win the World Series. But this is all done basically sort of like the same method that I sort of described when talking about the football or basketball team ratings. You start with the team ratings, you come up with game win probabilities, you simulate seasons. In this case, we simulated the playoffs. And You do that thousands of times, and then you see how many times a team wins the title. And so I've talked a lot about data visualization. I should mention that this visualization was not, these last two were not made by us. These were, we worked with the digital design team on these. We provided them the numbers. But one thing I did at ESPN was I created a ggplot theme called Theme ESPN. And basically, ESPN has an internal data visualization style guide, which are basically like guidelines when you're making any sort of visualization that involves data. It was pretty detailed. Basically, I started talking with the creative design team, and eventually realized that I could probably implement this in ggplot as a custom ggplot theme. All of the guidelines that they had laid out in this style guide could be implemented using ggplot. So I started working on that, and then actually after leaving ESPN, I did a public version that kind of borrows from ESPN, New York Times, BBC, and kind of just like my own preferences if I had any that were different than what they were doing. And that's on GitHub. So all of the visualizations that you see here that I've created either use theme ESPN when I was at ESPN, or if I created them, the visualizations after ESPN, they use this theme pub thing. So let's see. I think we're going to skip this in the interest of time. I'm going to skip ahead. These are some fun visualizations, but I'm going to skip ahead here. We kind of talked about this a little bit, but I just thought I'd mention it wasn't just the playoff format for the Major League Baseball that we had to rethink during COVID. There was all sorts of things that changed. Like all of a sudden, there's a bunch of new neutral site games. There's other new rules, like in baseball, I think extra innings, there was new rules, and then double headers were all 7 innings. There's a bunch of games. If they weren't at neutral sites, they might have been at a home team, at someone's actually home arena or home field, but those games did not have fans, or they had limited fans. And so if you have all these models that incorporate home field advantage, home court advantage, home ice advantage, what do you do in all these situations? So if you're at home but there's no fans, there's probably less of a home field advantage, and things like that. So so we had to make a lot of changes to the metrics, which is a little frustrating because like we got to do this now, but in 4 months, everything is going to go back to normal. And so you're making all these things that are only going to be temporary, and you'd rather be working on new things or something like that. But it had to be done, so we did it and made changes to our games predictions, in-game win probability, the team and player ratings, and so on. And I think I'll skip that. And then, so after ESPN, I joined Carnegie Mellon, and then Yale. And at some point during that time, I think maybe starting at ESPN, I started working on age curves, or just player performance over time. And this was Michael Shuckers and Michael Lopez, a project I was working on with them. And so, this is sort of like so what I've shown here is a plot of age and then standardized points per game for NHL players. Standardized meaning this was standardized differently for each season because there's scoring rates change over time. So we just did some standardization, which is I'm not going to talk about the details. So that's what this is. Each dot is a player from a particular season and the points per game that player scored during that season. And so if we just try to fit a curve to this data, we would expect, if we're talking about age curve or we're talking about performance over time, we would expect it to go up, peak somewhere. We don't know where. Usually in a lot of sports, it's like mid to late 20s, but it should peak somewhere and then it should go down. as the player gets older. We don't see that here. And this is a perfect example of a selection bias problem. So the only players that are left in the league over here are the players that were very good. And so we're actually seeing a flat curve here. In fact, it actually goes up a little bit, which doesn't really make sense if we're talking about performance over time in a league where, you know, most of the players are in their 20s and early 30s. So, you know, if we start looking at individual players, it becomes more clear that kind of what we'd expect is actually what happened. So this is just 4 players that I chose. You know, 4 good examples of players with long careers. We can definitely see a clear trend that, you know, they go up, they peak somewhere in their late 20s, I guess, and then start to decline in their 30s. And so this is a fun animation that we made, and this is just showing players. This is out of the league, in the league, and this is just showing players entering and leaving the league at different ages over time. And so, you know, this goes back to, I think it starts, I forget when it starts, maybe 96 or something like that. We'll see it go back around to the beginning in a second. But, you know, most players are out of the league in their early 20s or before age 20, at like age 18 and 19. Yeah, it looks like it went back to 95 or 94. But then, you know, sometime in the early 20s, they enter the league. And then, you know, once again, there's not a lot of players in the league towards the end, you know, after age 35. Some lasted forever, Mark Recchi. But just a fun animation showing the same thing that we kind of talked about on the previous slide. There is a weird part in the middle of this where all the dots go to out of the league. I probably could have skipped that season, but it kind of looked, I don't know, it looked fun. I figured I'd keep it in. That was the lockout season where there were no games played, so no one played in that year, in the 2004-05 season. So anyway, without accounting for player or doing some sort of data imputation for all the players who were not in the league, where their data is not observed towards you know, their mid to late 30s. Without doing that, you get that flat line. But if you do something like data imputation or just accounting for the player, you can get an overall age curve that looks like this. And I've had some students more recently do this in other sports. So this is golf. And this was interesting because he did 4 age curves, one for hits off the tee, one for hits, strokes that are approach to the green, around the green, and putting. And this was kind of interesting because the ones that kind of involve strength or athleticism, which would be like hits off the tee or approach to the green, do decline at older ages. And then around the green and putting are a little bit flatter. So the ones that are sort of like more skills and maybe more experienced, it looks like they peak later. In this case, it peaks a lot later. And then it doesn't tail off nearly as much as hits off the tee or approach to the green do. And then a student also more recently has one of our PhD students, Shinpei, has worked on this age curve problem in basketball, where load management has been like a big thing in basketball for a few years. And so anytime you're doing these age curves, most people are only looking at season level statistics. But if you're resting older players in back-to-back games, this inflates their season level statistics. So let's say it's points per game. If you play those back-to-back games, usually your performance is not as good in back-to-back games. So in the second game of back-to-back, and so that would tend to pull down your like season averages and points per game. But if you're not playing that second game of back-to-back, you know, this could be inflating your points per game in that season. If prior in your career, if you were playing all of those back-to-back games. So this would mean that age curves do not, if you're only using season level data, the age curves do not decline as quickly as they should be if you're not accounting for this load management issue. And so what he did was he used a different approach, a causal inference approach, and game level data to account for this. And so he has like 2 age curves here. And so this is like with 1 or more days rest, and this is for back-to-back games. And of course, you know, overall performance is just in general lower for back-to-back games. But it's also interesting at older ages, this is tailing off more quickly. This is decreasing more quickly. I think in the interest of time, I'm going to have to finish up soon here, I think. Russ, is that correct? So,
yeah, we've got till about 2:20. So if we leave a couple minutes for Q&A, but wherever you feel comfortable stopping, we're good.
Okay. Yeah, I'll go through this quickly. So this is a similar plot for WNBA. I'll skip this stuff. And I guess another thing, so prior to Yale, I mostly focused on hockey and basketball, and then the ESPN team was mostly focused on football, pro and college. Since coming to Yale, I've still done some stuff with those, you know, bigger sports, but I've also done a lot of stuff with just a wide variety of sports, like whatever students want to work on, basically, for their senior capstone projects or senior thesis projects. So I worked on projects related to soccer, diving, figure skating, gymnastics, swimming, squash, frisbee, tennis, sailing, and golf. And so I guess I will skip to here, just 1 minute. 1 minute summary of this. So I'm involved with this initiative called the SCORE Network. So a bunch of us from Baylor, Carnegie Mellon, Pitt, St. Lawrence, West Point wrote an NSF grant. And basically the focus of the grant is just creating content. So we're using sports analytics to encourage student interest in data science education. And so a big part of that is creating content that can be used in classes and workshops and so forth at the college level. And then, you know, I'm sure there will be some high school educators that use the material. If you're interested in any more information about the SCORE Network, we have a lot of partners across the country. And we're always looking for more partners. If you want more information, you can go to scorenetwork.org. And then here's some more contact information here. And so, yes, that's, I guess, as best as I can do for a 1 minute summary. And so I think we'll stop there.
All right. Well, man, that's a lot to take in. I kept seeing like visual after visual, animation after animation. At one point, I was live tweeting some of this as we were going along. I'm like, all right, man, you're just showing off at some point. But a lot of good stuff to chew on here. I will tell everyone that SCORE Network website, if you can go back a slide or two to that one is worth, you know, the faculty colleagues out there and students that are out there. I've played around a little bit on your website already, just a bit, and some of the modules for teaching and a lot of the data sets that are there. That is definitely an emerging, really, really useful resource. So I would encourage a lot of you to sign up and check it out and to consider contributing to. So yeah, let's open it up to questions here. If you would maybe use your Zoom reactions, maybe raise your hand or put something in chat, and we'll maybe just kind of go from there. So I see Dan Swenson says, oops, so where'd it go? Dan says, hockey has penalties, so a team might be down a player or two at various points in the game. It seems like a naive plus or minus stat would be biased against players who play on the penalty kill units and biased in favor of players who play on the power play. Can you adjust for that bias somehow so that the model doesn't always rate your penalty kill players as the worst players on the team?
Yeah, so what most people do is, and actually I didn't say this, but I should have, for that hockey adjusted plus minus model, it was only at 5-on-5, the first one. And then you could do separate ones that are for power play and penalty kill. That was like a separate, it was like a separate project that I had worked on. But yeah, you're right. You really do want to separate those things because, first of all, you don't want people who only on the penalty kill and don't play on the power play to be penalized. but also the style of play is different. So even if you're a good offensive player on the power play, you might not be as good. I mean, you're not going to be terrible at even strength on offense. But you might not be like one of the best players in the league on offense, just because the style of play is and the skills required to be successful during those times are quite different.
Well, other questions for Brian?
Yeah, and about the visualizations that you mentioned, I purposely I like talking about the projects where there's fun visualizations, so I focused on those more than I would otherwise.
Yeah, and I've already made a note and Googled the theme ESPN and your GitHub page. Let's see. Andrew Kerr says, on the aging curve projects, is it better to standardize by season or standardize by an individual player's performance over their career?
So we standardize by season just because, you know, if you're using data from different eras, you probably want to do that. Standardize by an individual player's career. So if by standardize you mean, so we did take into account an overall player ability. And so there is an adjustment for that. So it is, so I guess it's like sort of standardized in that way. But it is not standardized. So the way we standardize is within each season, we have some sort of standardization where basically, I think it was a type of Z-score, essentially. But either that, I actually don't remember. It was either that or we just made the average scoring rate the same for every season and just adjusted players up or down for each season based on some scaling factor. So that's what we did. I'm not quite sure what you mean by standardized by an individual player's performance, but if you mean adjust for how good a player is, so that he's sort of being measured relative to himself, then yeah, we kind of did that. The model is basically it's a regression model with one player intercept term and then a spline term for age. And so that player intercept term is the term that is sort of is modeling a player's overall ability, or at least not overall ability, but overall ability in that statistic, I guess.